Hello everyone, welcome to lecture 2 of week 3 in which we'll continue our discussion on synchronous generators. And in the previous lecture, which was the first lecture of week 3, we had discussed about the corresponding phasor domain equations which govern the operation of cylindrical pole synchronous generator, salient pole synchronous generator, and we also saw or concluded that the cylindrical pole synchronous generator circuit can be represented into an equivalent form, but unfortunately because there are two different reactances in a salient pole machine, xd and xq, we cannot have a equivalent circuit representation for a salient pole synchronous generator. So building upon that, in this discussion today, we will look at how do we evaluate the expressions for a real power, a reactive power delivered from a synchronous generator. These reactions or these expressions, by the way, could also be derived for a synchronous motor. So it can be applicable for any synchronous machine, but we'll keep our synchronous generator in focus. And then we'll also interestingly have brief discussion on what are these capability curves, and we'll continue on these capability curves probably in the lectures to come. So what we do is we start with the most complex case first, that is we consider a salient pole synchronous generator first, and for this salient pole synchronous generator we derive our power expressions, and from here if we have to find the corresponding power expressions, real and reactive power expressions for a cylindrical pole machine, then it is pretty obvious that in a salient pole machine we have two reactances xd and xq which are not equal to each other, whereas for a cylindrical pole machine the air gap being more or less uniform along the d axis or quadrature axis. For time being, if we neglect the variations in the air gap because of distributed rotor and stator slot windings, then in a cylindrical pole machine we'll have the same reactance along any axis. So for the power expression that we derive for salient pole synchronous generator, in those expressions if we equate xd and xq to be equal to each other, basically being equal to synchronous reactance, we automatically have our expressions for cylindrical pole synchronous generator. So what are those equations for a salient pole synchronous generator? We have discussed at length about this phasor diagram, why IQ current, which is component of armature current, lies along the induced EMF axis, and why the direct axis current ID, which is component of IA, is perpendicular to the induced EMF axis. Building on that, if we numerically represent the phasor diagram into two equations, one equation being along the IQ current, which is the equation number, first equation here, and the second equation which is along the direct axis, then we have this expression. And depending on what is the corresponding torque angle, which is always positive for generating mode, and depending on the phase angle, impedance phase angle, which is usually inductive load, so theta is usually positive in this particular sense. Depending on these angles, the corresponding ID and IQ components of armature current can be evaluated. So one thing before we go further into our discussion is, if we use these equations, which is ID and IQ equation, and try to see, do we have any ID and IQ currents in our first two equations? Then what appears is, the voltage drop which is along IARA with the cosine component, IA and the cosine component of theta and delta, it is nothing but IQ, whereas IARA drop with the sine component, so IA and sine theta, this current is basically equal to ID. So essentially if I rewrite the second equation, it is Vt sine delta plus ID RA equal to IQ XQ. And similarly, I can rewrite the first equation as EF Vt cos delta plus XDID plus, instead of this term, I can have IQ RA as the last term. So with these as our equations, which are also sort of discussed further. So if we focus, so with this, the first two expressions keeping in mind, if we focus on the last two expressions, we can expand the sine of theta and delta and the cosine of theta and delta into elongated forms, which would be the first two equations shown over here. And now if we multiply the first equation by sine delta and multiply the second equation by cos delta on both the sides and then add them up, I would essentially get my third equation. Similarly, if I multiply the first equation by cos delta on both the sides and multiply the second equation by sine delta on both the sides and then take the difference, I would essentially get the fourth equation. So essentially I am trying to represent Ia cos theta, which is generally a known quantity for the armature current, choosing terminal voltage as reference. I'm trying to represent the phasor currents or the armature currents quantities into the corresponding ID and IQ currents and the torque angle delta. Now, if we recollect our initial discussions of basic circuit principles, we had seen that the complex power is usually, or not usually, it is always the product of terminal voltage phasor multiplied with the conjugate of corresponding current. If we equate or correlate these quantities for synchronous generator, then we have chosen terminal voltage as a reference for all phasors, so its phase angle is 0. And assuming that the corresponding armature current is essentially, so there is a mistake here, I'll probably correct it here itself. I am assuming the current to be an inductive current or a lagging current. So essentially if Ia is equal to Ia at an angle minus theta, then Ia conjugate should actually be Ia at an angle theta. So essentially this negative sign here is a mistake. I am erasing it through this red color. So if I have the current to be lagging the corresponding terminal voltage, which is usually true for inductive loads, then the complex power is nothing but VTIA cos theta plus j sin theta, where j is the complex operator, essentially square root of -1. Now, in this equation, I can correlate or decompose into corresponding real component and reactive component. The real component is nothing but the per phase real power delivered, which is nothing but Vt Ia cos theta. And the imaginary component is per phase reactive power delivered, assuming that the generator is feeding in an inductive load, which is why I have the current as lagging in the corresponding terminal voltage. Then Q phi, which is per phase real reactive power delivered, is nothing but Vt Ia sin theta. And remember, I have already derived the equation which I am encircling here, where Ia cos theta and Ia sin theta have been expressed in terms of ID, IQ and torque angle. So from there, I can also rewrite or have expressions of P phase and Q phase in terms of terminal voltage, ID current, IQ current and torque angle. Now, if these expressions are so commonly available or useful, is that it, or do we need to do anything further? There is a catch here. The catch is, generally what we know for a given machine is the terminal voltage information. We can also know the corresponding armature current information, and from there it is pretty difficult to directly identify what is the corresponding direct axis current or quadrature axis current. Remember, these currents are fictitious currents. They are not actual currents flowing anywhere, not in the stator windings. The stator winding currents are still carrying armature current. For the sake of our discussion simplicity, we are decomposing the armature current into two components, ID and IQ, which are fictitious currents. So if we have expressions wherein we have fictitious quantities and they are difficult to identify, so there needs to be done something else so that we can get a better form of these equations, PQ and Q, per phase real power and per phase reactive power, which should not be in terms of ID and IQ. And that is where the next discussion comes in. So if you recollect the discussion that we had here, the equations that were rewritten in terms of this and this, so now it's time to reuse those equations. So let's see how do we reuse them. So the first two equations on slide number 3, we can rewrite them into these two equations which are shown over here. It's just a minor rearrangement. And now if we try to solve these two simultaneous equations for two unknowns, the unknowns are ID and IQ, because these are fictitious quantities. What one can usually get As I said earlier, one can usually get to know what is Vt, one can usually get to know what is the induced EMF, which is nothing but the magnitude being 4.44 n, phi f and f, where n is the number of turns on stator, phi f is the flux linkage, f is the source frequency, which depends on synchronous speed. So it's easy to know what is going to be the induced EMF magnitude. Also, it is useful to know what is the corresponding torque angle. So usually with these quantities known and xd, xq and Ra being the physical parameters of synchronous generators, which can be obtained from equivalent open circuit and short circuit tests. So it is now time to find ID and IQ, which are fictitious quantities in terms of usually known quantities. So if we solve these two simultaneous equations, we get these two equations where everything on the right hand side is usually known. The unknowns, however, or fictitious quantities, however, are ID and IQ. So when we know everything on the RHS side, we can substitute numbers here and also get these LHS quantities. So if we put these ID and IQ expressions into the expressions which we had seen in slide number 4, then plugging this ID current and IQ current into the positions over here, we will have the per phase real power delivered by the salient pole synchronous generator in terms of this particular equation here. One can again cross check the validity of these expressions, and similarly we can also have the per phase reactive power delivered by salient pole machine in terms of this form. So this essentially is the perfect accurate expression of a salient pole synchronous generator having winding resistance Ra and direct axis reactance Xd, quadrature axis reactance Xq, with terminal voltage being Vt, the phasor reference for all other phasors, Ef being the induced EMF, delta being the torque angle, and that's it. So from there, if we now try to sort of see, can there be any approximations there? So yes, usually in a well-defined or a properly designed machine, the armature resistance basically, a winding resistance basically, Ra is very small. So if we try to sort of neglect the resistance value in the windings in a properly well-designed machine. So if we put Ra as 0 in these expressions here, these two equations respectively tone down to these two forms. And from here, the expressions that are shown over here, they are the power delivered by the salient pole generator with 0 winding resistance. Now, if we have to find the expressions for a cylindrical pole machine, what we do, recollect, we will put xd is equal to xq is equal to xs. So if we do that in the expressions p phi and q phi shown over here, if we put xd is equal to xq, this term will become 0, and coincidentally we will be left only with this expression and this expression here. This is the expression for, this is the per phase real and reactive power expression delivered by a cylindrical pole synchronous generator. If we have a well-designed synchronous generator, winding resistance Ra is 0. So if we neglect that, then we have these two simple equations. Now these two equations, let's try to spend some time on them for a cylindrical pole machine. What we can infer here? The inference which we can get here is, if we have to find the maximum possible value of the per phase real power which can be delivered by a cylindrical pole synchronous generator, usually what is constant in a cylindrical pole machine, the terminal voltage is usually fixed because it is usually synchronized to a grid. Synchronous reactance is a physical parameter, so it cannot change. And as long as the machine is synchronized, the internal EMF would also most likely be fixed. What can change, however, is the value of the torque angle. So if you have to find the maximum possible value of real power delivered by the corresponding cylindrical pole synchronous generator, this maximum will happen only when sine delta takes its maximum possible value, because other quantities are more or less fixed, and sine delta will be maximum at a value of equal to 1, and for this delta would be equal to 90 degrees. So this is the corresponding maximum possible real power which can be delivered per phase from a cylindrical pole machine. Similarly, if it spends some time on Q phase, for an inductive load, the machine would be delivering reactive power. So for Q phase to be positive, Vt and Xs, as I mentioned, they are positive specification, they are not negative quantities. So if Q phase has to be positive, then it's pretty clear that EF cos delta should be more than Vt. That means the machine would be delivering reactive power. The machine can also absorb reactive power, and that is evident here from this expression. So if Q phase becomes negative, which means the machine is absorbing reactive power. So in that case, EF cos delta would be less than Vt. We will take up more about this expression of Q5 being positive or negative when we talk about reactive power control of synchronous generator in the next few lectures. So essentially, with negligible winding resistance, stator winding resistance, the real power delivered at stator is also fed through the air gap. So one can equivalently find the torque developed across the rotor or the corresponding equivalent torque delivered by the corresponding prime mover in generating mode, which would nothing be the three-phase total power divided by the synchronous speed dependent on the number of poles and frequency of the machine. For a round rotor machine, this I have already explained, that the maximum real power would be at an angle of delta is equal to 90, and any operation beyond delta is equal to 90 will lead into an unstable operation. That's the steady state real power transfer limit. We'll discuss more about this, that why delta is equal to 90 is the maximum allowable possible limit for the machine to safely operate. We'll discuss more about this in the last module of this course, which would going to be on stability analysis. So till that time, please have patience. We'll come back to this particular aspect, why delta is equal to 90 is the safest possible operation, and any operation beyond this would be unstable for the synchronous generator as well as the grid. We'll talk about it in the last module. And the other aspects I have already discussed. For non-zero real power transfer, generator delta should be positive, and that is the reason why for generating mode delta remains positive, because generator is supposed to deliver real power. So sine delta has to be positive. If phi delta has to be positive, delta should also be positive. In a synchronous motor, the real power is absorbed from the grid. So it basically converts electrical power to mechanical power, the synchronous motor. So in that case, real power is absorbed, so sine delta has to be negative. So in motoring mode, the delta will be negative, or sine delta will be negative only when delta is negative. That is the reason why torque angle is positive and negative in generators and motors. And the remaining last two aspects we'll talk more when we discuss reactive power control in detail. So till that time, please have patience. What we would take up in between is the notion of capability curve. In fact, all equipments, all electrical equipments, they have their own safe operating limits. And any machine which is designed to operate, it will always have certain suggested conditions or operating conditions beyond which, if it is operated, it would be detrimental for the corresponding element. Same is also true for a synchronous machine. And for capability curve discussion, we will consider the cylindrical pole machine specifically. Similar discussion is also applicable for salient pole machine, but that we will avoid for the sake of simplicity in this particular discussion. So for synchronous machine, there can be several such limits, or for any electrical equipment, there can be several such limits. Those limits come from three major components. First being the current. Any equipment can withstand a typical amount of current which it can run through, which it can deliver, or a conductor has maximum current carrying capacity. If the conductor carries current beyond a certain limit, the conductor gets heated up and it may melt down, so there may be rupture. Same is also applicable for voltage. Insulation strength decides what operating voltage a element or equipment can operate at. More is the voltage level, more is the insulation requirement, and over age or over time, these insulation properties, they sort of degrade. So basically the voltage built up is an issue in electrical equipments. And lastly is the amount of power which can be transferred or delivered or absorbed by a particular equipment without losing safety and stability. So similar restrictions also exist for synchronous machine. And if we have a mathematical plot or a two-axis plot wherein we can jot down these constraints or limits, then that is nothing but the capability curve. So essentially, locus or safe operating points depending on these constraints, if they are plotted on the complex power plane. By complex power plane, I essentially mean the x-axis referring to real power P and the reactive y-axis corresponding to reactive power. This is called as the complex plane in electrical power network domain. If we plot these safe operating points based on these constraints, then we'll have the capability curve. So how do these constraints or limits come in from? Specifically for synchronous generator, the same are shown over here. Every machine, synchronous machine specifically, would have maximum armature current limit. Armature windings, if they carry current beyond this limit, there is always possibility of the corresponding windings being melting or rupturing. Then we also have the maximum field current which can be induced. So indirectly, the maximum field current limit comes from the maximum rotor current limit, which we will see in the next lecture, not in this particular lecture. So the voltage limitation in synchronous machine specifically comes from the maximum rotor current limit. And third is the maximum power which can be extracted from this particular machine. So usually for the consideration of capability curves for cylindrical pole synchronous machines, we'll assume that the terminal voltage is fixed, it is operating at its rated voltage, and the synchronous reactance value is also fixed. So Vt and Xs, they are fixed quantities for this given machine. And every capability curve essentially pertains to this fixed parameters. If terminal voltage and synchronous reactance change, the capability curves will also change. They will also have deviations. So if we take up our first limit, which is the armature current limit for a cylindrical pole synchronous generator, any current beyond Ia max might damage the stator winding as well as the insulation and capability curve since they pertain to a particular terminal voltage. So this armature current limit in a way can be attributed to maximum MVA that the machine can transfer without violating or disturbing or damaging the winding or the corresponding insulation. So if Ia max is defined by the manufacturer and Vt, the terminal voltage, is known from the operation perspective of or the synchronization perspective of synchronous generator, we can have the maximum MVA as S max. Remember, this is apparent power, so there is no need of a conjugate here. S max is equal to Vt into Ia max. This is the maximum apparent power which is coming in or limiting by the corresponding armature current limit. So if we put our apparent power square is nothing but P square plus Q square. So essentially the armature current limit locus, if it were to be observed on a PQ plane, it would look like a beautiful circle whose center is the origin. Essentially, if I have P as Q axis, X axis, and Q on the Y axis, then the center of the circle is the origin. And remember, for circles, the typical equation on XY domain is x square plus y square is equal to r square. This represents a circle on the xy plane with origin as the center and small r being the radius. So for this locus of the armature current limit, Vt into Ia max is nothing but the corresponding radius. So that's what is mentioned over here. And the circle looks like this. This is the locus. All points which are inside this particular circle are safe operating points from the perspective of armature current limit for the cylindrical pole synchronous machine. Now, why did I talk about machine? I'll come to that in a moment. And on this plane, if I have to mark the corresponding impedance angle or load angle, which is theta, because if you remember or recollect, P, which is P over here, is nothing but apparent power into cos theta, and Q is nothing but apparent power into sin theta, where theta is the power factor angle or load angle. So is there a way to mark this load angle or impedance angle on this PQ plane? Yes. If we focus on the radius, which is Vt Ia max, then this angle, if it is theta, which is the impedance angle, the cosine component of this radius is nothing but the real power part, and the corresponding sine component, which is over here, is the corresponding reactive power part. So this representation of theta is nothing but the impedance angle, which is essentially what is shown in this over here. And now let's come back to why did I talk about this locus representing a safe operating limit from the armature current perspective for a cylindrical pole synchronous machine. Now, in a synchronous machine to behave as a generator, the corresponding real power should be positive. So, basically all points where P remains positive refers to the parts which are marked over here, and hence we would call this to be our points pertaining to a generator where P remains positive. In a motor, the real power is absorbed from the grid. So, all points on the left hand side which are marked over here would refer to the points pertaining to a cylindrical pole synchronous motor. And there's also one specific point. If this is the corresponding impedance angle, remember this angle is also known as the power factor angle. And for power factor to be equal to 1, which is also known as unity power factor operation, the corresponding theta has to be 0. So if theta has to be 0, then there is also a way to mark this unity power factor operation on this locus plane, which is essentially one which is shown over here. The yellow line, which is the line marked here, represents the unity power factor operation, and the blue and the green regions, they refer to generating points. The purple and the orange ones, they refer to motor points. And please have patience, we will talk about why have I written this as the blue part as overexcited or the orange part as overexcited, and vice versa, the green and the purple one as underexcited. We'll talk more about it when we discuss the reactive power control aspect. But just to give you an idea, the over and underexcited operation comes from the perspective that whether reactive power is positive or negative. For overexcitation perspective, the synchronous generator or synchronous machine is likely to deliver reactive power. So Q would remain positive, and that's the reason why the blue color region and the orange color region, the Q being positive, so machine is overexcited. It is delivering reactive power to an inductive load, whereas for the lower half, which is the purple and the green one, here Q is negative, so the machine is underexcited. That's all for today's lecture. We will continue this discussion on capability curves in the next lecture. Thank you.